We've seen how the average of independent random measurements behaves when we start with a normal distribution that describes the behavior of the individual observations that make up the average. The purpose of this video is to consider how averages behave when the distribution of the individual observations is something other than a normal distribution. Here are two probability density functions. In blue, we have one that describes the behavior of individual measurements, and it's a normal distribution. In purple, we have the distribution of the averages we might get if we took samples of size 9 from the blue density. And in another video, we saw the following facts about this purple distribution. The probability distribution of sample means is also normal. The normal probability distributions of individual observations and the sample means both have the same mean, the same center of the distribution. And the standard deviation of the probability distribution of the sample means is smaller, less spread, than the standard deviation of the probability distribution of the individual observations. And it's smaller by a factor of 1 over the square root of the sample size n. For these 3 points, points 2 and 3 hold in all situations. That's because they come from properties of expectation and variance that hold for any probability distribution, not just normal distributions. So now we just have to consider a more general version of point 1. In particular, we need to consider what if our individual observations follow something other than a normal distribution. So let's consider a distribution of individual observations that isn't normal. Many measurements have a right skewed distribution, so we'll use a right skewed distribution. Again, this is our probability distribution for how our individual observations behave. For this particular probability distribution, the expected value of a measurement from it is 5. So its mean is 5. We can observe random measurements from this probability distribution. They're most likely to be where most of the probability is, that is, towards the left of the values under the probability density function. I've randomly generated 2,000 individual observations from this probability distribution and plotted them in this density histogram. And we can see that, not surprisingly, the density histogram of the individual observations looks a lot like its probability distribution. Now, what if instead of individual observations, we take a set of observations, a sample, and find the mean? Here's a random sample of size 3. This particular sample has an average, or sample mean, of 6.58. Here's another sample of size 3. This one has a sample mean of 4.28. And we could do this again and again. I've done it 2,000 times and plotted the 2,000 resulting sample means in this histogram. Note that the vertical axis has changed on this plot to accommodate the histogram of the sample means. But it's the same probability density function of the individual observations. Some things to note from this plot. The sample means are likely to be close to 5. That's the mean for our individual observations. But they are more concentrated around 5. They have a smaller standard deviation than the individual observations. We've seen that before, but something new to note here is that the histogram is, while still right skewed, it's less so than the density function of the individual observations. Let's repeat this process for another 2,000 sample means, but this time each of our samples, instead of consisting of 3 measurements in our random sample, will consist of 10 measurements. Here's our histogram of sample means and our probability density function for our individual observations. The histogram of sample means is still centered at 5, but now it has even smaller spread with the larger sample size. And except for just a few values out here in the right tail, it's almost symmetric. Let's take this one step further and we'll increase our sample size to 25. And here's our histogram of the sample means. Still centered at 5, even smaller spread with the larger sample size. But now it has a symmetric bell-shaped distribution, a very familiar distribution. What we're observing is a result called the central limit theorem, and it's a central result of statistical theory. The central limit theorem tells us that regardless of the probability distribution of individual observations, averages of the observations have approximately a normal distribution. And the larger the sample size is, the closer the means are to a normal distribution. The remarkable thing about this result is that it holds however crazy or non-normal the distribution of the individual observations is. If it's really skew or has really large outliers or is widely bimodal, we would just need a larger sample size for the central limit theorem to kick in and for the normal distribution to be a good approximation to the probability distribution of the possible averages we could get from our random sample. A large sample size doesn't affect the probability distribution of our individual observations. That is what it is by its nature. But when carrying out a study, a researcher can choose the sample size. And if the researcher is working with averages and they have a large enough sample size, then the central limit theorem says that the averages will be approximately normally distributed. So now we can adjust our description of this distribution of the sample means as follows. Points 2 and 3 are still the same. They say averages have the same expected value as the individual observations that went into them, and the averages have less spread than individual observations. But for point 1, now we know that we don't need the individual observations to follow a normal distribution. As long as our sample size is large enough, the averages will approximately have a normal distribution by the central limit theorem. The central limit theorem guarantees that any random measurement that arises from adding up many different influences or from some sort of an average follows a normal distribution. So there are many examples of random measurements, lots of data that follow a normal distribution. And this is why the theorem and the normal distribution are so central to statistics.